Well, I have to thank all of you first for being here this evening. I can't tell you how gratifying it is to see this many people interested in Barton Springs. There's as many of you as there is at 4th of July in Barton Springs, and that's a big number. So thank you very much for being here this evening. Barton Springs and Austin seem inextricably linked. You know, anybody who grew up in Austin, who traveled through Austin as a child, even people who have never been to Austin, and they bring up Barton Springs. It's really pretty amazing. It's been called the soul of the city. It's been called Austin's crown jewel. And I'm not quite as wired for sound as I'm supposed to be.
Can you hear in the back okay? How about now? How about now?
That's all right. Right now?
That's it.
Is it working? Okay. Can you hear me now? Better? Could it be more?
Would you rather have this one?
Is this better? Can't fight a crowd.
You can try. So let's get rid of that one. No, that one stays. Sorry about that.
That's okay. We'll just blitz through all this introductory material anyway here. So Barton Springs. If you've recently moved to Austin, you might be wondering what all the hype is about. Barton Springs is in the news. It's on the city council agenda. It's an election issue. And those of you who have lived in Austin for a while may know something about Barton Springs and understand a little bit of what the hype is about. But I hope that all of you will go out this evening with a new way, perhaps, of looking at Barton Springs. Now, it's more than just the world's coolest swimming pool. It's about the springs, but even more, the springs is just the tip of the iceberg, or the tip of the aquifer, that, if you will, because the aquifer that delivers the Barton Springs, water to Barton Springs, stretches all the way from south of Austin, from Kyle, all the way up to Austin. So it's really a whole natural system that has taken literally millions of years to come into being. And we're lucky enough to be living in the here and now at a time when we can enjoy it. So the first thing I want to ask is, how many of you have been swimming in Barton Springs, ever? Yay! Okay, I figured most people would raise their hands. If you're not raising your hands, don't be embarrassed, but get yourself down there this weekend and get in the water, because you're in for a treat. Okay, so let's raise the bar a little bit higher. How many of you have been swimming at Barton Springs on a hot summer night between 9 and 10 o'clock at night, when it's free and the lights are on and it's like you've been transported into some alternate resort community that only people in the know about? You should check it out. It's really a great experience. It's like a big party down there. Okay, even harder. How many of you have been swimming at Barton Springs between 5 and 6 in the morning? I see a couple of hands out there. That's a really magical time of day, too. It's still dark. It's incredibly quiet. The herons are all out. All you can hear is the quiet splash of those die-hard swimmers as people move up and down the pool early in the morning like that. So if you go to Barton Springs and you go swimming, it doesn't take very long. Even one visit will give you the idea that this is really more than just a swimming pool, because the water is flowing. You can swim day or night. The water is always a pretty much constant 70 degrees. You can swim in the summer. You can swim in the winter. It's not chlorinated. It's not just a swimming pool. And as a matter of fact, about 350,000 people visit Barton Springs every year. So it's a well-loved Austin icon. And we're not the only ones that like to swim in Barton Springs, because Barton Springs and the aquifer are a natural system. It hosts its own animals and plants that live in the springs. This is Austin's most well-known denizen of Barton Springs. This is the Barton Springs salamander. It's a federally listed endangered species. There's another salamander that lives in the springs, the blind salamander, and there's also lots of native plants and other types of animals that live in the spring and aquifer system. Now, in case animals are not really your thing, we can be more pragmatic and talk about some of the importance of Barton Springs and the aquifer that feeds it. And one of those issues is drinking water. As you noticed in the film clip, I mentioned that Barton Springs provides an important part during some times of the year of the drinking water that serves Central Austin at the Green Water Treatment Plant. A lot of people aren't aware of that, but Barton Springs is really the only continuous source of water to Town Lake. Even perhaps more importantly, the aquifer that feeds the springs is the only source of drinking water for about 45,000 people, and that number's growing as Austin continues to grow. So I've mentioned the word aquifer a couple of times. What is an aquifer? Quick definition here. An aquifer is a body of rock or sediment underground, obviously, where there are sufficient little spaces within the rock that it can hold water. And not only can it hold water, but the water can move through the rock, and you can remove it from the aquifer in economically feasible quantities. And you can define economically feasible for yourself. It's a personal definition. Now, the aquifer that feeds Barton Springs is a special kind of aquifer. It's a karst aquifer. And karst terrain is terrain where the landscape has been formed by the dissolution of rock. Well, what do you mean rock doesn't dissolve? Well, most rock doesn't dissolve, at least not at the surface. Granite doesn't dissolve, sandstone doesn't dissolve. But limestone, which is made of the mineral calcium carbonate, limestone's the kind of rock that we have around Austin. When you go by a big road cut and you see all that white rock, that's limestone. And it dissolves in the presence of acid. If you drop hydrochloric acid on limestone, it'll fizz. And that fizzing is the gas that's produced as the rock dissolves. Now, you're going to tell me, well, we don't have hydrochloric acid in the environment. No, we have rain. And rainwater is very slightly acidic. And once that rain gets into the soil and interacts with the bacteria and the organic matter, it's even more acidic. So that slightly acidic water can go down little cracks and fissures in the limestone and dissolve the limestone away. And the more it dissolves away, the more water can get in. And the more water can get in, the more limestone can dissolve away. So we have what's called a positive feedback here. And so the rock is dissolving away into these pipes and conduits that might be a fraction of an inch wide, or they might be a giant cave, and that's what the water can flow through. Now, karst is not exactly rare. We have karst here in Central Texas, it's in Florida, it's in Tennessee, it's in Pennsylvania, it's in France, it's in England, it's in China, it's in New Zealand, it's in Australia. Why is it when you open a standard college hydrogeology textbook on hydrogeology, there's probably one page devoted to karst? Well, it's because karst doesn't play by the rules. What's the difference between a karst aquifer, like we have here, and the kind of aquifer that 326 of your 327-page textbook is going to talk about? So let's imagine that you have a big block of sand, a big box of sand over here. That's your sandstone aquifer. Sandstone makes a great aquifer. If you've ever tried to lift a bucket of sand or a bag of sand after it's gotten wet, you know it holds water. It's really heavy. Let's over here say that we have a big block of concrete. Now, it's not karst yet. Let's make it karst. Let's take a sledgehammer and smack it so that we have a bunch of fractures in that concrete. Now let's pour some acid on it and dissolve out the concrete around those cracks. Now we've got karst. Now let's rain on both of them, and let's see what the water does. The water will flow slowly through the sandstone, and it'll flow pretty much the same in all the different parts of the sandstone. In the karst, the water is going to go through those dissolved out areas, and it's not going to be flowing at all in the part of the concrete that didn't break. This is karst, this is sandstone. One of the differences is that water flows really slowly in sandstone, and it flows really fast through these fissures in karst, just like through a pipe system. Now, a couple of scientific terms that explain why it's not in the textbooks. If you go in the sandstone, pretty much anywhere in the sandstone aquifer, the water is doing pretty much the same thing. It's flowing in at the same speed with the same kinds of characteristics. The flow is very different in the part of the karst aquifer that's not fractured and the part of the karst aquifer that is fractured. And this difference between different parts of the aquifer is called inhomogeneity. Technical term meaning it ain't the same here as it is there. Okay. When you're trying to predict what's going on in an aquifer, you don't like inhomogeneity. It's poorly behaved. It's difficult to handle and difficult to predict. So we don't put it in the textbooks. Okay, anisotropy, another technical term. What that means is there's a preferential flow direction to karst. It's anisotropic. Sandstone, there's no preferential direction of flow. It's isotropic. What do I mean by direction of flow? Let's imagine we take our 2 blocks and we put them on end, and we rain down on them again. You're still going to get water in the sandstone that's flowing from the top to the bottom under the force of gravity. But now in our Karst Aquifer, if we stand our block on end, these fissures and fractures are going to be more horizontally oriented. The water is going to flow in that direction. It's not going to flow from top to bottom. It's going to follow the fractures. That's called anisotropic. There's a preferential flow direction. And again, this makes karst a little bit unpractical to use the standard mathematical models that have been developed to predict what's going on in the subsurface. There's a famous karst hydrogeologist, Tim Quinlan, and he said that karst is the twilight zone of hydrogeology. So we have to come up with some other tools. We have to be detectives, and we have to use some other things that we can look at to try and understand how karst aquifers work. Now, that doesn't mean it's bad if you have a karst aquifer. They're extremely productive aquifers. If you sink a well down and you hit one of these big water-filled conduits, you're going to get a lot of water. This is in the southern part of the Edwards Aquifer down closer to San Antonio. This is the famous Catfish farm well. And when this well was drilled, it was the most productive well in the world. So karst wells can be extremely productive. However, the characteristics that make them productive mean that we have to be careful because they're very vulnerable to contamination. What are some of those characteristics? Well, to start with, most limestone has very thin soils. If any of you live in the western part of town and you try and do any gardening, you know that you don't have very thick soils. And soil is very helpful in remediating contamination because a thick soil layer will do several things. It will slow down contaminated water as it moves down, give it time for the bacteria to maybe break down some of those contaminants. It can filter out contaminants. Some of those contaminants will sorb to the soil particles. But if we have very thin soils, then we don't have that opportunity for remediation of contamination before it gets to the aquifer. Sometimes water just goes straight down one of those infiltration features that have dissolved out of the rock. So there's a direct conduit from the surface to the aquifer without any kind of change in the quality of the water. And finally, as I mentioned before, water is flowing through these dissolved out pipes in the rock, and it's moving very quickly. So that if you have like a contaminant spill, you may not have time to do anything about it before that has entered the aquifer and maybe moved several miles away. Well, when Austin was first settled, we didn't have to worry too much about contamination because the city was not settled over the aquifer, which is down in this direction here. And that was in the 1850s. But since then, urbanization has grown, and now we've got civilization down here on the recharge zone of the aquifers. We'll talk about a little bit more. And the activities that go on at the surface because of the characteristics of karst mean that what we do at the surface, we're going to see in the quality of the water as it moves through the aquifer. Now, it's no accident that Austin settled near a spring. Most of central Texas was settled because of a series of springs. And so geology, what happened millions of years ago, affects why we all live here today. This green area is called the Balcones Fault Zone. And because of reactivation of the Balcones Fault Zone, many, many millions of years ago in the Oligocene and the Miocene, these springs formed. And central Texas has been settled around these different springs. Now, the part of the aquifer we're going to be talking about this evening is this part here between the Colorado River and a groundwater divide down near Kyle. And this is the part of the aquifer that feeds Barton Springs. Now, to better understand how this aquifer is working, let's imagine that we could take a big slice through it, like a slice through a layer cake, and look at it from the side so that we can see from the bottom to the top what the aquifer looks like. Okay, here's just a diagram, a kind of a cartoon of what that slice might look through. And we can take a look at how this cartoon is now, the schematic diagram, and try and reconstruct the geological events that happened to form the Barton Springs portion of the Edwards Aquifer. So about 100 million years ago, in the Cretaceous period, when dinosaurs roamed the earth, central Texas was a shallow tropical sea, kind of like the environment around the Bahamas now. And there were lots of organisms that had calcium carbonate shells, like mussels and clams, and when they died, their shells went down and were deposited on the bottom of the shallow sea. And then they were precipitated or cemented together with precipitating calcium carbonate, and that makes limestone. And if you go out today and you look at a road outcrop, if you look at the limestone, that's the Glen Rose limestone or the Edwards limestone here in town, you can see fossils of some of these animals. These mussel shells are still there, embedded in the rocks. So originally, we had the Glen Rose limestone deposited, and directly on top of it, just like a layer cake, we had the Edwards limestone. And after that shallow sea receded and some of the top of the Edwards eroded away, other geologic units were deposited on top of that, like the Del Rio clay as shown here. So then we still had a layer cake kind of arrangement with the younger deposits up at the top. During the Oligocene and Miocene periods, the Balcones Fault Zone was reactivated, and the result was that the rocks more toward the east dropped down, just as is shown here. So they started to be offset, and these faults formed that run from pretty much from south to north, and they're pretty much vertically oriented. And the result of that was that we have the older rocks, once there was some erosion that took the top off, we have older rocks exposed to the west, and then the next oldest, and then the more younger, and then the youngest rocks are exposed to the east. When that happened, the faults were exposed at the surface in the Edwards limestone, and water could get in. What happened when water got in? That's when we started forming the karst, because that's when we could dissolve away, that's when the rain could dissolve away the limestone and karstify it. How is that expressed at the surface? Well, let's take a look. Here's our cross-section again, and here's a map view. So the Glen Rose limestone in our cross-section is expressed on the map as this big area here. This is the outcrop of the Edwards limestone, and this is the area where it's overtopped by these other permeable units. So what happens when it rains is water flows across what we call the contributing zone. That's the Glen Rose limestone, and water doesn't really infiltrate into the Glen Rose very well. So it flows on the surface through these familiar sounding creeks, largely from west to east, until it gets onto the Edwards limestone. Whoops, what happens then? It infiltrates, goes down into the rock, disappears unless there's a whole lot of flow, makes a sharp turn, and heads towards Barton Springs, following those faults and fractures. So now you have a little bit of idea of what the whole aquifer that feeds Barton Springs works like. Let's take a look at the spring system itself. Barton Springs system is really made up of 4 different main spring orifices. There's the spring that everybody knows about that's in the swimming pool, but there's another spring, Old Mill Spring, Eliza Spring, and a 4th spring that's not on this photograph that's called Upper Barton Springs. There are salamanders that live in all 4 of these springs, and they're all hydrologically connected. The flow, when the flow in one goes up, the flow in the others go up. So Barton Creek here is flowing in this direction. When Barton Creek gets to Barton Springs Pool, it doesn't actually enter the pool, and that's a misconception a lot of people have. Barton Creek is, in fact, when it's flowing, routed around the pool through a bypass underneath the sidewalk, and then it flows back into the creek bed down below the pool. It's only under really extreme conditions that the flow is high enough in the creek to overtop this dam to fill up the bypass and actually flow into the pool. These other little springs are not as big as the main spring, but they're pretty nice little spots. Upper Barton Springs is kind of interesting because it doesn't flow all the time. It only flows when the water table in the aquifer is higher than average, when we have higher than average flow. And you can see it upwelling here. This is on the banks of Barton Creek, upstream of Barton Springs Pool. Barton Creek, if it were flowing, would be flowing down here in the bed. And Upper Barton Springs has not a whole lot of flow, but it does support a salamander population when it is flowing. Now, Old Mill Spring is downstream of the pool on the south side of Barton Creek, and it's really hard to see where the water is upwelling here. There are a bunch of little upwellings in the middle of the spring, and it has flow that's about 10% that of the main spring. Eliza Spring, you've probably seen if you've ever bought a hamburger or ridden on the train. It's that concave kind of amphitheater-like structure that's over there behind Abel's Hamburger Stand. And it hosts a very healthy population of salamanders, particularly thanks to some habitat restoration that scientists from the city of Austin have recently done. Now, I said during normal conditions, Barton Creek doesn't flow into Barton Springs. Well, sometimes in Austin we have non-normal weather conditions. And every once in a while, there's nothing you can do. And Barton Creek floods the whole pool area. And when it does, one of the lasting effects that it leaves is some of the sediment that's coming in from Barton Creek, which is coming through a pretty urbanized area, does get deposited in the pool. Now, some water obviously gets in the pool too, but the water has a much shorter residence time. It flows out and kind of cleans itself out pretty quickly. But the sediment from the creek can stay in the pool for quite a long time. And so if the sediment is contaminated, that's an area of concern for us. Now, we've been enjoying Barton Springs as the human race for quite a long time. There were Native American tribes that had settlements around Barton Springs. And there was a Franciscan mission that was founded near Barton Springs in the early 1700s. But Barton Springs, as we know it today, started to come into being in 1837 when Uncle Billy Barton bought the land around Barton Springs. And in the late 1800s, it was popular as a swimming hole, as a picnic area, as a camping area. And in about 1917, Andrew Zilker gave the land to the Austin School District, which then turned around and sold it to the city as a park. So it was at about that time that we start to see Barton Springs as it is today. In the 1920s, the city enlarged the pool. They put in the sidewalks. The bathhouse that you're probably familiar with if you've been to Barton Springs was built in 1946, so it's almost 60 years old. So there's been a long history of interaction with the citizens of Austin and the city of Austin enjoying Barton Springs. Okay, let's get to the science part here. We've talked about the history of Barton Springs, the geological history, and a little bit of the cultural history. Let's talk about the present right now. What do we see in the water? Well, I work for the U.S. Geological Survey, and we have a pretty active water quality monitoring program at Barton Springs. We do cooperative studies with the City of Austin, the Texas Commission of Environmental Quality, and other agencies. And so I'll be describing some of the results to you that we've gotten fairly recently. So one of the first things that we can measure in the water are what we call physical parameters. Those are things that you can just go out, stick a probe in the water, and measure something like temperature. Any of you could go out and measure the temperature in the springs. And what we have is we have probes permanently installed in the springs that are doing just that. They're collecting measurements continuously. And every 15 minutes, those measurements are averaged, and the data is recorded in a data logger, and also that data is then put on the web. Any of you can log on to this website, and you can find out what any of these parameters are at Barton Springs any time of the day or night, 365 days a year. So what are some of these things? Well, of course, we're interested in how much water is coming out of the springs. And in fact, there are some interesting statistical tools that we can use to look at the long-term flow record and use that, because we're karst detectives and we don't have some of these other tools available. We can use the flow record to learn something about how water flows through the aquifer. Other tools that we can use are things like temperature. Conductivity. Conductivity turns out to be really important, and let me describe to you what it is. Conductivity is a measure of the dissolved solids in the water. What do I mean about that? Isn't the water pure? Well, just about no water is pure. Only distilled water is pure. When you buy a bottle of water, that's not pure water. It's got all kinds of different dissolved species in it, things like calcium and sodium and chloride. All of those are naturally occurring species in water in the environment. Conductivity is a measure of how many of those dissolved solids those are. Those solids are negatively and positively charged, which means they can conduct electricity. That's why you don't want to be in a big swimming pool in a lightning storm. So the more dissolved solids there are in the water, the better it can conduct electricity, and the higher is the conductivity. Rainfall has pretty low conductivity. It's as close as you can get to distilled water in the environment. So conductivity, measuring this, is a very good tool for us to figure out how recently the water got into the aquifer. If it came in rain, it's going to have low conductivity. As it spends time in the aquifer, it's going to be dissolving away the rock, getting more dissolved solids, and have a higher conductivity. So we want to look at water quality in the pool if we want to characterize water quality under different kinds of conditions. One kind of condition is what we call base flow, and that's when it hasn't rained in a while, the aquifer water is just kind of slowly at a steady state coming out Barton Springs, and then the other condition, obviously, is in response to a big rainfall. So let's take a look at what some of these parameters look like under base flow. These measurements were taken in July of this year. Remember, we got a bunch of big rain in June. But in July, things were pretty much steady state. Spring flow here is about almost twice the average. The average spring flow is about 50 cubic feet per second at Barton Springs. So those big rains we got in June resulted in really high spring flow this summer. Sometimes it's even as low as 20. Conductivity, it's not doing much. Just kind of steady state conditions. And the turbidity, how cloudy the water is steady here at about 3 turbidity units. That's in fact a little bit high, but that's because during this big rain in June, we got a lot of sediment that washed into the aquifer, and it takes a long time for that to move through the aquifer and wash out. But what happens when it rains? Well, the big rainstorm that we got was in June, on June 8th of this year. Let's take a look at what those same 3 physical parameters did after it rained. Okay, here it comes. Whoa! Okay, what happened? Well, first let's take it spring flow. How fast was the water coming out of the aquifer? This is thanks to a velocity meter. This is a new instrument that Will Asquith at the USGS and a couple of our other folks have put in to measure velocity, the speed of the water as it comes out of Barton Springs. And it increased after about 2 days by almost 50%. Now look at conductivity and turbidity because they're mirror images of each other. Here we see this less conductive rainfall. It must have come in through the creeks, moved through the aquifer, and came out of Barton Springs really fast. We're talking like a day here for that water to move all the way through the aquifer. And at the same time, the turbidity went up. Well, what's that mean? This is the sediment that was in the surface creeks, because you go out in a big rain in Austin, that water looks like chocolate milk in the creeks. It's infiltrating into the aquifer, and it's coming out of Barton Springs. And again, as we see the turbidity go up, the conductivity goes down. They're mirror images of each other because they're both a signal of what's going on at the surface. We can take a closer look at that. Here in blue, what we're looking at over time, this is flow in Barton Creek. Big high water, a couple big high water peaks. And you see that echoed in the turbidity coming out of Barton Springs, and we can measure the lag time here between the two. So again, by looking at the water chemistry, we can learn something about how the aquifer works. Okay, now another natural kind of parameter that we can measure at the springs are major ions. Now these are not physical parameters. You can't just go out and stick a probe in the water. We have to collect samples and take them to the laboratory and analyze for these things. But these are the dissolved solids I was talking about, the things that are in your bottled water that you buy. And the water at Barton Springs has a signature. And as a matter of fact, each of the springs has its own special signature for these dissolved ions. These are some samples that were collected last summer. The USGS did a 2-month pilot project for the Texas Commission on Environmental Quality, and we went to the springs. We sampled all 4 of the springs every 2 weeks for a 2-month period during base flow to get a picture, what's the water quality like during base flow. Let's take a look at sodium. Eliza Spring and Main Barton Spring look just about identical. Upper Barton seems to have a little bit less sodium, and Old Mill has almost more than twice as much sodium as the other springs. So these springs are hydrologically connected, yes, but they're not identical, and they're not plumbed identically into our underground conduit system of the aquifer. And we can find out a little bit more about why these might be different by looking at what happens in these springs when you lower the pool and you let the water out. Now the pool staff does that a couple times a year to clean the pool. And think about it. You've got 9-10 feet of water on top of the spring in the pool. What happens if you let all that water out? The spring flow rapidly increases, and what I think is happening is some of the water from the eastern part of the aquifer where there's very little circulation, there's much higher dissolved solids. In fact, we call that the bad water zone. It doesn't mean the water is contaminated. It just means there's a lot of dissolved solids. I think some of that is coming into the spring. So you see when they draw the pool down, these samples are collected every 2 hours, the sodium content in the main spring increased. Now, the sodium content in Eliza's spring increased too, but look how much later it increased. So even though they started out with the same concentration, they didn't behave similarly. So that tells us, again, it's another clue to try and tease out how these different springs are connected. Old Mill also got more sodium-like, and Upper Barton didn't do anything at all. This suggests that Upper Barton isn't really getting any water from the bad water zone, and these other springs are. So this is just some of the types of tools that hydrogeologists use to better understand the aquifer. Now let's move on to something we can measure that's kind of something natural and kind of not. Nutrients. Nutrients occur naturally in the environment. These are things like nitrogen and phosphorus that are the nutrients that plants need to grow. And they do occur naturally in the environment. When plants break down, they have nitrogen in them. Phosphorus comes out of rocks. But we add to the plants, to our gardens, to make them grow. We put on fertilizer. We put on nitrogen and phosphorus. And also, wastewater contains nutrients. Animal waste contains nutrients. So there are excess nutrients in the system that we put there. Now, if nutrients make plants grow, why is that a problem? Well, the plants that they make grow in water are algae. And when you get an algal bloom, several undesirable things happen. First, the algae clouds the water so that the sunlight can't penetrate to the bottom, and the natural plants that normally live there don't get enough sunlight to live. But another thing that happens is that as that algae decomposes, it consumes the dissolved oxygen in the water, and that's the oxygen that the aquatic species like the fish need to breathe. So basically, the algae is suffocating the fish. And if you get a big algal bloom, that's called eutrophication, and it's a dead system. The only thing that can live in there is algae. So we want to measure nutrients. So here's a graph of nitrate plus nitrite, two different nitrogen species, two different nutrients at Barton Springs. Again, these are these same 5 visits that we did every 2 weeks last August and September. And the 4 springs, the bright green is Upper Barton Springs. The dark blue is Main Spring. We're working our way downstream. The turquoise is Eliza Spring, and the purple is Old Mill. What do you notice? Well, first thing that I notice is that if you ignore what's going on at Upper Barton Springs, not much is going on. It's very constant at a pretty low level, less than 1.5 milligrams per liter, and the drinking water maximum contaminant level for drinking water is 10. So it's a nice, low, steady level at base flow. But what's going on at Upper Barton Springs? Well, we already saw Upper Barton was kind of weird. Now it's looking really weird. It's got, in one case, nitrogen levels that are twice what they are in the other springs. It looks like this spring is more vulnerable to contamination from the surface than the other springs. And we see some other results that corroborate that. Something else that we monitor for on a regular basis are pesticides. We're concerned about pesticides because they're toxic. They're designed to be toxic. Insecticides are designed to kill insects. Herbicides are designed to kill plants. That's why they were invented. That's why we use them. But when they're in the water system, they're also going to have perhaps toxic effects on other species that weren't meant to be targeted. So we're concerned about pesticides in our water supply, obviously. So we go out and measure for pesticides. Most pesticides that we use today are very, very soluble in water. And the problem with that is it means we find them just about everywhere. The USGS, in a nationwide study, found 1 or more pesticides in 99% of the surface water samples and almost half of the groundwater samples. So in the Barton Springs, during this base flow period we were sampling, we detected fairly frequently 3 different pesticides. They're all herbicides. They're all closely related chemically: atrazine, promazine, and simazine. So here's what atrazine looks like. Again, these are the same 4 springs. Those ghost boxes is where we didn't detect them. And we detected atrazine in Upper Barton Springs in every single sample we collected. So again, it looks like Upper Barton Springs is more vulnerable to contamination than the other springs. Another thing that's kind of interesting here, notice on the 4th site visit, this concentration went way up. Well, I'll tell you a secret. It was supposed to be under base flow conditions, but we did get a little rain a couple days right before this site visit. And you know what? Even though it wasn't even enough to make the creeks flow, we saw it reflected in the amount of atrazine that we saw coming out of Upper Barton Springs. Now, are these concentrations high? the maximum contaminant level for atrazine in drinking water is 3 micrograms per liter. So we're at about 100 times less than the maximum level that you can have in drinking water. So the good news is that these are very low concentrations. The bad news is it's there. What happens when it rains? So that was base flow. Let's take a look what happens when we get these big slugs of surface water moving through the aquifer. This is a storm that we sampled in 2000, and we collected samples at Barton Springs. This is 1 day, 2 days, 3 days, 4 days. And we saw atrazine. This is called a breakthrough curve. This is like a slug of pesticide that has come in at the surface and moved all the way through the aquifer to come out at Barton Springs. Now let's take a look at these concentrations. The last ones we were looking at were 10 times lower than this. So we have a maximum concentration here of about 0.5, still less than 3, which is the maximum contaminant level for drinking water, but getting kind of up in that range. Another thing is that the concentration at the peak here was 75 times higher than the base flow concentrations. So if we're only measuring concentrations during base flow, there might be a lot of things going on at the springs that we don't know about. And this was still high a week after the rainfall. It was still about 35 times higher than it was during base flow. So it's up to us as water quality detectives to design a sampling strategy that lets us know what's going on at the springs. Let's say you think, okay, I want to know what goes on after it rains. I'm going to wait a day after it rains and I'm going to go out and collect a sample. What would you see? You'd see this sample. Would that give you a real picture of what's going on in the aquifer? It's kind of a needle in a haystack. Okay, so another group of compounds that we've been analyzing for are called VOCs, volatile organic compounds. What are those? A volatile organic compound is a contaminant that evaporates easily. Can you think of a contaminant can you think of a substance that evaporates real easily? About gasoline. You spill gasoline, it evaporates. It's a VOC. And gasoline compounds are among the compounds, benzene, toluene, ethylene, xylene, and MTBE also, that we are looking for in spring systems. Now, these compounds may evaporate really easily, but they also dissolve pretty easily, and once they're in the groundwater system, there's no place for them to evaporate to. So they are often detected in groundwater. Other popular VOCs are industrial compounds, things that we use to clean metal parts or clean floors, or in dry cleaning, VOCs are used. So there were 2 VOCs, tetrachloroethylene, which is shown here, and chloroform, which were detected in every single sample from every single spring. So it looks like Barton Springs, even at base flow, is being affected by some of these VOCs. Now again, these are very low concentrations. The maximum contaminant level in drinking water for tetrachloroethylene is 5. We're down at about 100 times less than that. Interestingly, again on this 4th site visit, we saw something strange happen. But this time it's the opposite of what we saw. This time it's Upper Barton Springs that didn't change, and it's the other 3 springs that did. And again, we can use the clues we get from things like this to try and figure out what the source of this contaminant is. It doesn't look like Upper Barton Springs is plumbed into where that source is, and the other 3 springs are. And yet one more class of contaminants that everybody's really interested in right now, ever since somebody found a fish up in Lake Waco that had Prozac in its tissues, we're interested in a group of what we're calling emerging contaminants. These are chemicals that we all use in our daily life, and we ingest them, or we wash with them, or we clean with them, and they either get flushed down the toilet, or they go down the sink, or they go down your shower drain. They go to the wastewater treatment plant where they're not effectively removed, and they go into the environment. We don't necessarily know if these even have adverse effects, but we suspect that there's something that we should be keeping track of. Things like pharmaceutical products, antibiotics, hormones, pills that you're taking. Antibiotics may be great if you have an infection, but do we really want antibiotics in the environment where the bacteria, the natural bacteria, can become resistant to some of these drugs? So we're going to be sampling for different what we call wastewater indicators at Barton Springs over the next year in a year-long project that we're doing for the Texas Commission on Environmental Quality. So we can't talk about water quality without talking about sediment too. Sediment and water are part of water quality, part and parcel. And sediment quality at Barton Springs hit the front page of the Austin American-Statesman about a year and a half ago. So let's see if we can, let me tell you and see if I can clarify a little bit more what some of the issues regarding contaminated sediment are at Barton Springs. Fortunately, it turns out that really for about the past 5 years, the USGS has been sampling suspended sediment in a program for the city of Austin. Suspended sediment in our urban creeks after storms, and suspended sediments that are coming out of Barton Springs. And we analyze a group of contaminants that, because of their chemical properties, stick to sediment better than they dissolve into water. And these are called hydrophobic, which means water, fearing water. And they're called that because we find them on the sediment. We don't find them on the water. Some of the contaminants of the most environmental concern on the EPA's toxicology lists are hydrophobic contaminants. So they definitely have concern in the environment. And these include things like heavy metals, some organochlorine pesticides like DDT, which is still out there in the environment, and polycyclic aromatic hydrocarbons, which is the contaminant that was featured in the Austin American-Statesman story. And we'll hear more about PAHs in just a second. Let's start with metals. Turns out in Austin, we really don't have a big metals contamination story, and that's good news. I'm going to show you a couple slides that have some moderately complicated graphs, for which I apologize, but let me just talk you through it real quick. Everything over here on the yellow side is our 4 springs. Everything over here on the blue side is one of 3 surface creeks. This is Barton Creek at Highway 71, where there's not yet a bunch of development. And then Barton Creek just above Barton Springs Pool in a much more urbanized area. And Williamson Creek at Manchac Road, which is also in a very urbanized area. And the dots are green, yellow, and red based on some sediment quality guidelines that tell you whether these are not very contaminated or really contaminated as far as how they might affect the animals that live down in the bed sediment. Now, interestingly, for several of the metals, we saw higher concentrations coming out of the springs than we saw even at the urbanized surface creeks. And we thought, what's going on here? Is there a source of contamination we don't know about? Is there some sinkhole somewhere that's filled up with batteries that's contaminating the aquifer? But because we're water quality detectives, when we analyzed the geochemistry of the sediment, it became clear that these elevated concentrations of arsenic, nickel, chromium, and cadmium were because of the natural geochemical qualities of the sediment in the aquifer. They just naturally tend, because of their characteristics, to concentrate these metals. But for 2 other metals, lead and zinc, we saw the opposite. We saw higher concentrations here in the urbanized areas. And when we looked at the geochemistry of the sediments, we couldn't explain it. So we know that these contaminants must be coming in from urbanization. And in fact, zinc and lead are the 2 metals most closely associated with urbanization in the United States. So that was no big surprise. When we look at the organic contaminants, we see something a little bit different. We saw DDE, which is a breakdown product of DDT, on most of the samples that we collected from the surface streams. And we're seeing a little bit of it coming out from the springs, very low concentrations, but this is a man-made chemical, and so if it's into the environment, it's because we put it there. Now, PAHs, polycyclic aromatic hydrocarbons, these have a natural source. PAHs are formed whenever you burn anything that has organic matter in it. So if you have a forest fire, it's going to create PAHs, but at pretty low concentrations. Natural soils have very, very low concentrations of PAHs, like we saw coming out of the springs. So the good news is PAHs coming out of the springs are very low. The bad news is PAHs in our urban creeks are very high. Where is that PAH coming from? Well, PAHs are a lot of urban sources. The usual suspects for PAHs is any time you combust organic matter. It's in car exhaust. It's in rubber tire particles. It's in asphalt. It's in cigarette smoke. It's in cigarettes. The cancer-causing agent in cigarettes is a PAH. It's in a burnt steak. So there's lots of sources of PAHs out there. And they are formed, there's a whole bunch of them. They're formed by different configurations of this six-sided benzene ring. So every different configuration you can think of for benzene ring gives you a new PAH. And PAHs are the largest class of suspected carcinogens, cancer causes. They're bad players. Okay, the story and the statesman. Let's get to the nitty-gritty here. The city of Austin sampled some tributaries upstream of Barton Springs that feed Barton Creek that had incredibly high concentrations of PAHs, much, much higher than we see even in really contaminated sites. And the question was, where are they coming from? Because most of these urban sources, while they have PAHs in them, do not have PAHs in concentrations high enough to explain this. So the statesman postulated that there was a secret underground waste dump that nobody knew about that had PAHs in it, and that's where they were coming from. But I think that based on some very astute observations by the city of Austin, we don't have to look that far. We just have to look in the surface. You can buy a product to coat your parking lot called Seal Coat. And seal coats come in two flavors. There are coal-tar-based seal coats and there are asphalt-based seal coats. And as you'll see in just a minute, coal-tar-based seal coats have a lot of PAHs in them. And seal coat is put on your parking lot to beautify it because we like nice, black, shiny parking lots. And don't laugh. If you go on the website, that's the first thing that all the seal coat companies say is make your parking lot look like new. Secondly, it is claimed that it protects the asphalt from breaking down. And I'm not an asphalt engineer, so I'm not even going to touch that subject. But if you put seal coat on your parking lot, the manufacturer recommends that you do it again in 2 to 3 years. Why? Where does it go? Okay. 2 flavors of seal coat. What's the difference between them? Coal tar and asphalt. They look the same. They're black. They're shiny. They come from 2 very different processes. They have very different chemistries. Coal tar is produced by the steel industry as a waste product when they turn coal into coke or gas. Asphalt comes from the petroleum industry during the distillation process. Coal tar, 50% PAH or more by weight. It's a hazardous waste. It's a known carcinogen. It has a lot of PAHs in it. Asphalt also contains PAHs, but at concentrations much, much lower. Coal tar-based sealants that you can hire somebody to come and paint on your parking lot, or you can go to your favorite home improvement store and buy in a big bucket, contain 20 to 35% coal tar. And you can do the math, but we're talking weight percent of coal tar in these products. Geographically, most coal tar sealants are used in the east. That's where the steel industry is. Most asphalt-based products are used in the west. That's where a lot of the petroleum refineries are. More than a coincidence? Hard to say. In Austin, we have both of these sealants available to us. You can request either a coal tar or an asphalt-based sealant, and you can choose between them at the home improvement store. So the city did just that. They went out and they got different sealants, and they analyzed them for PAHs. Let's take a look at the axis here. This is percent. Think 1% PAH isn't such a big deal? Well, let's think back to the concentrations that had the red dots in the creeks that we were looking at before. Those units were micrograms per kilogram. 1% is 10 million micrograms per kilogram. 1% of PAHs is a lot of PAHs. Coal tar-based sealants have a lot of PAHs. Okay, so the sealants have PAHs in them. We put them on the parking lot. They're supposed to stay there. How important is this in the environment? Well, to try and figure that out, we went out in the environment and we picked out 13 parking lots in Austin that are currently in use. Some of them were sealed with coal tar sealant. Some of them were sealed with asphalt sealant. Some of them were just plain old concrete, white lots. And some of them were asphalt lots that weren't sealed. You don't have to seal your asphalt lot, just regular old asphalt. And we manufactured rain by using a hose and a sprinkler and distilled water, and we rained on the parking lots, and we collected the sediment, the little particles that flowed off, the kind of particles that would flow off the parking lot when it rains. And we filtered them out, and using one of these Teflon filters here, and we put them in a bag, and we sent them to the lab. And here's what we got back. Okay, the red and orange dots are our data. And the yellow dots are some literature sources, literature figures out of the scientific literature for urban PAH sources. On the far left are the particles that we washed off the coal tar sealed lots. There's our 10 million micrograms per kilogram. That's 1% PAH. These are asphalt-based sealed lots, and these are unsealed lots. So the concentrations of PAHs that are being found in urban creeks pretty much all around Austin look like they may have to do with the coal tar sealant that we put in parking lots. So it looks like this PAH contamination problem is not specific to Barton Springs. It is a problem at Barton Springs just like it's a problem everywhere in Austin, and it's probably a problem everywhere in Texas, and it looks like it may be a problem on a national basis. So we've been able to pinpoint one smoking gun for PAHs in the urban environment, and identification is the first step to a solution. Okay, so to wrap up here, I hope you're not disappointed. The title of the talk was The History and Future of Barton Springs, and I didn't talk about the future. And that's because I don't know the answers. What we know is what happened in the past. We know from the history of the aquifer how it formed. We know how the water moves through it. We know what's happening right now. We know that we have low levels of contamination, but we see higher concentrations after it rains. We're starting to understand more about how long it takes for those to move through the aquifer. What's going to happen in the future? That's up to all of us. That's up to the people that make public policy decisions, and it's up to the citizenry, and it's up to everybody who can affect how decisions are made in a place like Austin. So the history and future of Barton Springs, I can't answer the future questions, but hopefully you'll take some information about Barton Springs that will allow you to make your own decisions and form your own opinions about what's going on in the system. I'd be happy to take questions. What about runoff from Asphalt Roads? What question is, what about runoff from asphalt roads? Asphalt, that was one of the data points that was on. Let's see if this will let me go back. Runoff from the asphalt parking lots, which is similar to the asphalt that's used on roads, does have PAHs in it, but at much, much, much lower concentrations. And they weren't statistically any different than what was just washing off the concrete parking lots. The sealer, yes, the sealer is something that is put on to improve the appearance of the parking lot and in an attempt to protect the asphalt from weather and things like leaking motor oil.
Go ahead and look that.
Okay. Is something going to be done about getting rid of coal tar sealants in Austin? The city has proposed a voluntary ban at this point on coal tar sealants in Austin. They'd also like to see more studies done. We're right now doing a study for them using some of this stuff that's coming off parking lots and seeing how toxic it is to some of the organisms that the salamander eats. But I think that this is the kind of issue that people that are informed and can communicate their support to the city might be able to make a difference. Yes?
Why were there no results for velocity and turbidity on July 17th?
Why were there no results for velocity and turbidity on July 17th? Which year? What? Which year? This year?
Whatever slide that was.
Possibly because possibly because sensors weren't working. Possibly because we got data that was suspect because the instruments weren't working like they were supposed to. And so if we get data that we don't trust, We don't publish it. Will, do you know anything about why on July 17th we didn't have turbidity?
The velocity itself was, I believe, was continuously recording through the flood events this summer. But the discharge itself, maybe a little confusion on one of the slides. No, discharge itself, USGS pulls discharge data off the web when the pool is under flood flow conditions or drawn down conditions, because we don't have a good understanding of the hydraulics yet.
So again, if it's data that we have reason to not have full confidence in, then we don't publish it. Yes?
Barbara, the study on the parking lots, the coal tar runoff that you and Pete did, there was some, you were out of town actually at the time that you talked about that in the press. There were some mistakes in the data that were presented or put out in the press release and the report. I mean, you're good scientists. How did that happen?
How did that happen? There was a single mistaken data point in the report, in the press release that went to the Statesman. What happened? Oh, I'm sorry. He was asking in a story that the Statesman ran on the results of our parking lot sealant study. There was a problem with the data that was initially presented in the first story that was in the Statesman, and then they came out with a front page article the next day or within a couple days. I was out of the country, but it was very shortly thereafter, pointing out that there's a problem with the data. What the problem with the data was, there was one data point where we had reported total PAH as a true total PAH. In other words, all the PAH compounds, we summed them up, and that was total PAH. Elsewhere in the report, total PAH has been expressed as the sum of just parent PAH compounds. So it did make a difference in the number. It meant that instead of being, I think, something like 17 million, it was 10 million. From a personal point of view, that's kind of like saying this person was only stabbed 32 times instead of 48 times. It was unfortunate, and it was the kind of thing we should not have allowed to happen. Every once in a while, something like that slips through. But I think what's important is to even take that correction to the data in context and still understand that the results of the study, the conclusions of the study, weren't changed at all by changing that one data point. Yes?
Does the PAH affect the salamander population?
Does the PAH affect the salamander population? We believe that it does affect salamanders. It's a very toxic compound. There's some anecdotal evidence that when high pH concentrations have been found in the pool, there were lower numbers of salamanders. And that's why we're doing this toxicity study right now, to look at what the effect that PAH has on the animals that the salamander eats. Because one of the most important things that it might do is kill the salamander's prey. And if the salamander doesn't have anything to eat, then they don't do very well. So it's a good question. Yes, ma'am?
Would there be any reason to favor like coal-tar-based seal coat as opposed to asphalt? Because I mean, the asphalt would be better. Wouldn't it be more safe?
The question is there any reason to favor coal-tar-based sealants over asphalt-based sealants? Apparently, the coal-tar-based sealants are more resistant to things like spilled gasoline and leaking motor oil than asphalt-based sealants. However, virtually everyone on the West Coast seems to be using the asphalt-based sealants. So some of it may be an economic issue as to whether in some parts of the country one product is more expensive than another. There's quite a bit of literature on it on the web. There are some of the advantages of the asphalt-based sealants, as they say, when you apply it, you don't have to wear nearly as much protective clothing, which is indeed an advantage. And so there are pluses and minuses to the two different products. Yes, sir.
I'm going to take a question from the internet, from someone watching the webcast. If PAHs are harmful to the environment and the animals in the environment, why are coal tar sealants legal?
Well, there's lots of things out there that are harmful to things in the environment that are legal.
That question comes from Katie. Here's another question from Mark. How exactly does the water remain warm in the winter?
It's insulated. The water in the aquifer? The water in the aquifer is pretty much the average temperature in Austin. And once water gets into the rock, it's once it's down deep in the aquifer, it's insulated from those changes at the surface from cold weather and warm weather. So what it is kind of the average of the temperature. So the average temperature in Austin is about 70 degrees.
Great. One more question. It's about sunscreen. Can that pollute water in Barton Springs?
I don't know the answer to that question. We haven't looked at sunscreen. We are, one of the contaminants that we're looking at in these emergent contaminants is DEET, the product that's in mosquito repellents. And boy, that's ubiquitous. We find that everywhere. Yes, sir.
Earlier in the presentation, you mentioned Atrazine. Is that a tree killer or a general vegetation killer? What kind of activity?
Atrazine, I believe, and I may call on Lynn to help me, is a pre-emergent herbicide. So in theory, you put it on the ground before the weeds come up to prevent them from coming up. It's used, the only product that I know of that I've seen, when you're a hydrogeologist, you do weird things. You go to Home Depot and you read what's in all the pesticides. The only product that I've seen that contains atrazine in Austin is Scott's Weed and Feed. But there's plenty of that available. Yes, sir.
You mentioned how fast the water is moving through the aquifer from the contributing streams. Does the city of Austin take any consideration as concerns? Because if you have a major pollutant going in one of those streams and it gets to markets in miles per day, it goes into the Barton Springs and potentially to part of our water supply. Has the city considered anything to prevent or contingency plans for that?
The question is, are there any contingency plans by the city if there was to be a spill of some kind of toxic chemical in the creeks to prevent it from infiltrating and coming out at Barton Springs? Is there anybody from Nico? I saw you somewhere. Do you want to address this question?
Actually, there is the city is under the conditions of the Habitat Conservation Plan that allows the city to leave the pool open to recreation, despite the fact that there's an endangered species in there. As part of that, there is, we're developing a catastrophic spill plan that is quite extensive for particular types of toxins and petroleum products, and then basically we'll be, calling all of you and asking you if you really want to be on our volunteer phone list, so that if this is about to occur, you go racing out to try to deal with the spill. But that's something the city does have currently.
So if you couldn't hear her, she's saying as part of the habitat conservation plan that's being developed for the salamander, they're developing a hazardous spill plan. Yes, sir.
Yes. Is there any way we can help, I guess, clean up the PAHs from the environment? Like remove the sealants without contaminating the environment with any more toxic chemicals?
Boy, the question is there any way to remove the PAHs from the environment without creating a bigger problem than we already have? Is that pretty much what the question is? You'd probably have to ask a pavement engineer, and there are pavement engineers. And I have learned more about pavement than I ever thought I would know. But I don't really know the answer to that question. But I think I'm going to tread on sensitive territory here. I'm not supposed to make recommendations. But from a common sense point of view, it seems to me that one place to start would be to not put any more on. Yes, sir.
Why are some faults in the surface springs and some allow water?
That's a good question. Why are some faults in the surface springs and some faults allow water to, some of them act as, we say, a sink or a source? Why does water go down some and come out of others? Ooh, it all has to do with geology. We need to know what's going on in the subsurface. And a lot of times it has to do with how those faults, how the movement along those faults, the juxtaposition of different kinds of rocks has created. So you can imagine that if you have a nice karstic conduit or bedding plane in one chunk of rock and it comes to a fault where it's suddenly abutting a rock that's not karstified, that water has to go somewhere. And a lot of times it'll go up and that'll be a spring. But if you're in an area where, say, the water table is quite a bit deeper, then there's no pressure, there's nothing preventing the water from from going down. So it really has to do with the structural geology of the subsurface and the water table levels that will affect that.
Here's a question from the internet from Jill. Can you drink the water straight out of the springs?
Most of the time. When I would not drink the water straight out of the springs is right after it rains. And that's not because of any of the contaminants that I showed you. It's because of bacteria. And in Karst, I didn't talk about bacteria tonight. We ran out of time. But one of the things that Karst aquifers are very vulnerable to is contamination by bacteria. And boy, there's a big problem up at Brushy Creek about 10 or 15 years ago with cryptosporidium in their water supply after a rain. What happened is I think that the municipal wastewater treatment plant overflowed, flowed down into the karst. Cryptosporidium came up in people's wells, and hundreds of people got sick. So we know that there are high bacterial counts in Barton Springs after it rains. If the water's cloudy, I wouldn't drink it. If it was clear, I would drink it. Yes, sir.
You've shown that the pHs are high in sealants. You've also shown that the pH is high in Barton Springs, but the connection between the two and the flow seems a little unclear to me.
Well, in fact, the question was, we know that there are high concentrations of PAHs in the sealants, but in fact there are not high concentrations of PAHs in Barton Springs. The sediment that's coming up out of the springs, in fact, has very low concentrations of PAHs. So if there are PAHs infiltrating the aquifer, we are not yet seeing the effect at the springs. There have been some tracer studies done by the City of Austin, the Barton Springs Edwards Aquifer Conservation District, that you can see on the VSEACD website, which are really interesting. Under different flow conditions, water moves at different speeds through the aquifer. So during low flow conditions, when it hasn't rained for a long time, the water level is low, the water's not moving very quickly. And it may take days or weeks for the water to move from, say, Barton Creek out Barton Springs, but it can take a tenth of that time under high water flow conditions.
I think you misunderstand the direction I was going with that. With everything that flows in the aquifer, I can see how you can model that, but has anyone modeled the flow from the city, say the sewer system that we're supposed to be sending our water to before it goes anywhere else? From there to the aquifer, because you're going and running tracers straight in the aquifer, and I don't see you running tracers in the city for me to go from the city into the aquifer.
The question is, let me see if I've got this. Have there been tracers from the city wastewater system to Barton Springs?
You've got water on from the parking lot and a sewer system between the streets. So is the city releasing it into the aquifer, at the top of the aquifer, and then we're watching for it to show up in Barton Springs? Or?
Most of the city wastewater treatment plant discharges downstream of Austin into the Colorado River. So in terms of water treatment, mostly what we have in the aquifer are the municipal utility districts. And then we also have septic systems, and then we have sewer pipes which are run down the creeks. Now, I believe that when there is a suspected leak in the sewer system, they do some dye traces, but I don't think that anybody has put a bunch of dye in the sewer system and seen if it comes out at Barton Springs. We have our dye trace expert up there. Nico, am I correct in that?
Yeah, that's right. In most applications, the amount of leakage is relatively small, and it's not a very good application of tracers. Maybe a better application is something that Jay Banner's doing with isotopes, looking at the isotopic signature of water from urban structures and looking for that in the water. Whereas a tracer, you're going to just get a small amount of it. You won't pick it up. It's probably not the right application of a groundwater tracer for what he's talking about.
Okay. Good question. Sure. The question is, how does the water break the limestone? How does the water and rain break the limestone? The limestone broke originally because Earth shifted, like an earthquake, and that creates faults. And those faults are, you can imagine, if you take a rock and you crack it, you're going to have a really tiny crack. Well, what happens is rainwater comes down and it infiltrates into that crack. And the rainwater, which has hydrogen ions, which are an acid, interacts with the rock, which is calcium carbonate. And there's a chemical reaction that goes on that dissolves the rock. Kind of like an analogy would be, what happens if you take a glass and you put salt into it. The salt dissolves, right? That's kind of what's happening when it rains on the aquifer. The rock itself is dissolving away, it's going into the water, and it washes away, and it just leaves a hole. Does that answer your question? Okay. Yes, sir.
Have you seen any correlation in spike in turbidity after a storm event and the city of Austin's measurement of high bacteria in springs?
The question is, do we see a correlation between high turbidity and high bacteria in the springs? I personally have not done that analysis, but I've done similar types of analyses in other karst systems, and in fact, there is a very close correlation between turbidity and bacteria, to the point where a number of places around the country are now using turbidity as a surrogate for high bacteria counts. They're measuring turbidity continuously and using that as a signal for when the turbidity goes up, we better tell all our water treatment plants, people need to be prepared that there may be high bacteria counts. So there is a well-established correlation between bacteria and high turbidity. Yes?
When water comes bubbling out of the springs, the Barton Springs, how long has that water been underground?
That depends. The question is, when water comes bubbling out of Barton Springs, how long has that water been underground? Let's talk about the average water particle, because there's probably some water that's been in the aquifer a lot longer than other little particles of water. It really depends on the water table level. So when the water table level is high, the water is moving through the aquifer much more quickly, and when the water table level is low, it's moving through the aquifer more slowly. But the dye results from the dye tracers that we have, let me give you an example of some of those extremes. And Nico, again, correct me if I'm wrong, but from some dye tracers that were done at Onion Creek, dye that was put in at Onion Creek under low water table levels was seen at Barton Springs several weeks after the dye was injected. So that water took about that long. It had lived in the aquifers for 3 weeks, say, more or less. Under high water table conditions, it came out in a matter of days. So that's a real change in the velocity. And that's not even, we have yet to do a dye trace, and I think this would be fascinating, to do a dye trace when it's actually raining. So that's when we really have things infiltrating and shooting through the aquifer. So that's yet another tool that we could use to better understand the relation between what goes on at the surface and what's coming out of the springs. Yes, ma'am. If we had no contact with the aquifer from now on, would it fix itself? Would it clean itself? Probably, if we gave it enough time. Just about every contaminant, no matter how persistent, eventually breaks down. But for some things, we might be talking a really long time. But yeah, eventually everything will move through the aquifer at some point. But that's probably pretty unlikely that we're all going to pack up and go live somewhere else. We like it here. Yes?
Geology question.
Okay.
You had the faulting that occurred. Was it a reactivation that you said? That fault was being reactive. So when was it active before, and what caused that period of reactivation?
The question is, I talked about the Balcones fault zone becoming reactivated. When was it activated originally, and what caused the reactivation? Is there a geologist in the house?
I think we can call upon two structural geologists here, Dr. Mark Helper, Dr. Sharon Mosher.
I love these lectures. We have the best audiences. Mark, you want to handle that one? When was it?
I'm not actually aware of one period of movement on the Balcones fault zone.
I thought that the original structure was created during the Ouachita.
There's an older break there that would have been maybe more on the order of 300 million years instead of 60 million years. So maybe originally 300 million years ago, and then more recently about 15 million.
And do we know what caused the faulting 60 million years ago?
16?
In the more recent faulting.
As more and more sediment came into the Gulf.
So it was subsidence in the Gulf from the weight of new sediment sediment coming in cause that down dropping. Yes, sir.
The conditions that cause the spring to be closed for use, are they always going to be related to rainfall and high bacteria levels, or are there other conditions that would close the spring?
Well, the spring was closed 1.5 years for quite a long period while the city was evaluating the PAH contamination. So that had nothing to do with rainfall. That was because people were very alarmed about what they read and about the PAH concentrations. And so the pool was closed until the city and a very large body of experts took a look at all the data and determined that there wasn't a problem. So yes, under some conditions, the pool will be closed not because of rainfall and high bacteria, but because of other concerns. Sometimes the pool is closed while they clean it. Every Thursday the pool is closed during the day while they clean it and get all the gunk out and make it so that we can use it. And then twice a year it's closed for a longer period for a more thorough cleaning. So there are different reasons that the pool has been closed. Yes?
I hear a lot of discussion and concern about the silting up of the pool, particularly in the deep end, and that it may be suffocating plant life and fish aquatic life. Is it a problem? And am I correct in remembering that some years ago, I believe some developers threatened to sue the city because they were lowering the pool on a weekly basis to clean the deep end? And so that practice was suspended except for a few times a year. Is that what's causing the problem with the buildup of siltation, and what do you recommend?
I'm going to ask Lori Grieve, who is actively working with the pool staff on the siltation and cleaning problems, and I'm going to ask her to answer that question. Speak loudly, my dear.
Okay. For those of you that have ever been in a house that was renovated, you have an idea what it ought to be, what you want it to be, and it was pretty darn clean and your refrigerator worked and everything, and then they come in and they rip it up and it looks horrible. And then eventually it starts looking nice again. So that long-term view is how I want you to interpret what I'm going to say. So the interaction between drawing down the water level in the pool to flush things out, to clean it, and then stopping that practice, and then an influx of sediment coming in the pool and silt coming in the pool and settling. Yeah, those two things are related, because to draw down the pool, you're opening gates in a dam. And that's a creek, in a sense. There are dams on either end, so we've taken something where you had flow that came racing down the creek periodically. We had lots of rain. There you go, you know. We took what was that natural process and we inhibited it. So it's very logical to open the gate so that you have water that's moving in a direction to help flush it out. But you have to balance how quickly you open those gates and how much you drop the water level. And at the time, I believe, at the time that all of the controversy and attention was put on listing the salamander as endangered, the mechanism in the pool for opening those gates was all or nothing. You open the gates, the water rockets down, bam, there you go. And it's in a matter of hours, minutes, that water level will drop 4 feet. Salamanders just don't follow the water that fast. So by doing it in that mechanism, it drops it too fast. That's why you had to sort of stop with that part of it until adjustable gates could be put in, and until we could begin to understand and predict how much do you open the gates that will lower the water level slowly enough, a certain distance, number of inches, given a level of discharge. With that information we now have by practicing over the last year, we can go back to allowing the gates open some, to let that system act more like a creek, to flush out some more of the sediments, and then close them. So it's, you know, it's like this progressive thing. And with that, what you're going to see is as things move through there, it may look worse for a while, because things are going to start moving around and popping up in different places. The benefit of opening the gates is that now there is more fauna in the pool. So, you know, it's kind of this, doing a little bit of a balancing act. So hopefully, does that sort of make sense?
I understand your conclusion. Is it good to lower the water frequently and clean it out, or if it's done slowly?
Yeah, it depends on how you do it. It depends on the path of the water flow through the pool. Basically the mechanism that you do it. It's good to allow the flow to move through the pool. Yes, that's good in terms of the habitat. The frequency is the part that's hard to predict because of not having tried to do it enough, not being able to regulate how that works, given how much discharge flow we have and how many animals are actually in there. So it's just going to take some time to learn how to do it, but it would help some to be able to flesh it out more.
Okay, we're approaching our witching hour, so I'm going to, let's take 2 more questions. Yes, sir. He put his hand up really fast.
On the parking lot experiment, did you do an experiment where you looked at parking lots that had been recently sealed versus parking lots that had been sealed 2 years ago or many years ago, and did you see a correlation between the PAH levels and how recent the parking lot had been sealed?
The answer to your question is yes, kind of. We picked parking lots of different ages. We didn't have the funding to do a study where we could do a huge number of parking lots. The analyses are really expensive. But we did choose parking lots, some of which had been sealed as recently as a couple of months previously, and some of which had been sealed as long ago as 5 years ago. And if you go to the USGS webpage, there's a data report on this parking lot study, and there's a table that gives you the ages of all the different parking lots. We didn't see any correlation between the concentrations and the age of the sealant. So the parking lot that had been sealed 5 years ago had higher concentrations than some coal tar sealed lots that have been sealed more recently. So although intuitively I would have guessed it might be that right after it's sealed you might see elevated concentrations, but it doesn't appear that after that curing period you see much of a difference.
When that indicated it's another source?
Pardon me?
Wouldn't that indicate it's another source? Because anytime you have something that would adhere to something, as it pulls away, it should have an exponential decay in the amount that washes off. So if you're getting consistent levels of wash off, that's either saying that you're creating matter or there's another source.
Well, we're talking about a concentration, not necessarily about a yield. And as long as the sealant on the parking lot is still available, it may be that just a constant rate that this stuff becomes mobilized at a constant rate. I agree with you, eventually enough of the sealant should wash off the parking lot so that there isn't any left, but most people reseal, well, not everybody, but many parking lots are resealed by the time that happens. If there is another source of PAH, we haven't been able to determine what it is, because the parking lots that were not sealed receive all the same types of urban inputs as the sealed parking lots. So they have people driving on them. They have cars with exhaust and dripping motor oil and tire particles and atmospheric fallout. So there's really the only difference that we know of between the parking lots that we sampled was the actual surface type. Now, we have started doing, we had some test plots at Mueller Airport where a commercial sealant company came out and put out fresh sealant on 4 different plots. We had 2 coal tar plots and 1 asphalt plot and then 1 plot that wasn't sealed at all. And we washed those off 3 times each over about a 2-month period, and we did see a decrease in the concentrations of those. But we have not been able to continue washing those off. The study didn't include the funding to be able to continue to do that every 6 months. I agree, I think that would be a very interesting experiment to do.
Who has the last question for Dr.
Moll? Yes, sir.
I would imagine that this is a fairly large volume use of coal tar, and you were saying that it was a byproduct of some industrial processes we had. Is there a use that would not release PAHs into the environment at all?
My understanding is that, and this is based on some conversations with an industry representative that I had, the use of coal tar in sealant products, because I originally thought, if we ban coal tar and sealants, is it going to send the steel industry to its knees? apparently this is a drop in the bucket compared to other uses of coal tar. The main use of coal tar is by the aluminum industry, and they use it somehow in the manufacture of, boy, I hope I don't put my foot in it, but I think it has something to do with electrodes.
So that doesn't release PAHs into the environment?
I have not looked into that particular industry at all. So I can't answer how the use of coal tar by the aluminum industry affects the environment. But I do know that there are other uses of coal tar. Additionally, we now import coal tar. We do not create enough coal tar in this country with our steel industry, because the steel industry volume has gone down over the years, that we are now importing coal tar for our uses. So I don't think we're going to send the steel industry to its knees. Okay.
Before we thank Dr. Mahler, I want to just note that it's really good to see so many people so concerned about the environment we live in, sticking it out here for so long and asking good questions and saying, keep on looking into this and keep on asking these good questions about it. I also think we're fortunate to have a panel of experts from the city and it's really great to have all these people here to weigh in on this. And finally, I think we're really lucky that we have someone doing world-class research on this in our own backyard, and the stuff we swim in. Let's thank Dr. Mahler.